Okay, so new chapter. What is this chapter about? That's maybe the biggest thing to sort of get out of the way first. What we're going to do in this chapter is actually figure out what molecules look like. In order to do that, we need to figure out how atoms, there's a very logical way that they bond together. We have to figure out how the atoms will connect together, so we'll give you some rules for that. So we'll figure out how the atoms connect, and that gives us kind of a two-dimensional shape that we'll draw it on paper. Okay, and then what we'll do is we'll look at what those things look like in 3 dimensions and talk a little bit in this chapter about how that affects their properties. Okay, so there's just a couple of things that we kind of need to go over before we really get into this chapter. Just review from the last chapter. We know about valence electrons, those highest energy level electrons, and we're only going to be doing the main group elements and not the transition elements. And so for valence electrons, the number of valence electrons is always the group number. So if you're calcium in your group 2, there's 2 valence electrons. If you're carbon in your group 4, then you're 4 valence electrons. So that's the thing that you need to remember. It's the same as the group number that's given here. Okay. The next thing that to understand is that if you pick up electrons, you're going to have a negative charge, and that's how we get anions, right? So we add electrons. And when you're going to make a cation, you have to give up electrons because the electrons leave and leaving behind the positive charge, so we're going to be removing electrons. The last thing to talk about, and in fact we'll talk about it in more detail in this section, we're going to talk about 8 valence electrons being a good thing, and 8 valence electrons will put it in group 8, right? So that's the noble gases. So there's a little statement I wrote down here when I was writing these notes. Seems like there should be a lot more, but everything else just builds off these basic ideas about gaining and losing electrons. So we'll start with uh, a tool that was developed by Lewis to draw structures with, and these things have become, because Lewis did a lot of this work, it became known as Lewis structures. And so the first thing you have to understand is how to draw a Lewis dot formula for an element. Okay, so the way you do it basically is you write the element symbol, right? Place 1 dot on each side of the symbol, and it helps. This is what I did here. Just imagine there's a box, and there's 4 sides to a box. And so what you're going to do is take the electrons and put 1 electron on each side until you get all 4 sides filled. And then if it has more than that, then what you'll end up doing is you'll end up adding dots next to dots, and you'll end up pairing them up until you get up to 8. So this is again this idea of 8, the octet, being a good thing. You have 4 sides. If you put 2 pairs of electrons on each side, that becomes an octet, or becomes 8. Okay. Okay, so I pulled up the periodic table, and what we'll do is just do nitrogen right away, and so I can show you how this kind of process works, and then we'll look at what it looks like for making different kinds of ions. So, for example, here's nitrogen, right? And on the sort of newish periodic table, we have the number 15 at top, but now in the older ones it'd say 5a. So it depends on which periodic table you're using. But just if you subtract 10, then it's 3, 4, 5, 6, 7, 8. Those are the number of valence electrons for those nonmetals on that side. And for the metals that is over here, right on these guys, then it's 1 and 2. And we're not going to concern ourselves with the ones in the middle. I think I said that before. So let's go ahead and we'll go back to the slide or the notes, and we're going to do the Lewis dot formula for nitrogen. So let me erase. That was kind of weird, and start this again. We're going to have nitrogen, right? And then we think about it being like in a box, right? And we're going to put in 5 valence electrons. So we have 5 that we have to deal with. So we're going to go 1. Now, it doesn't matter where you start. It doesn't matter if you go clockwise or counterclockwise. You could pair the first 2 if you can foresee that already. It doesn't really matter, but it's going to look something like this. What has to be true, right, is that you have, this is a pair of electrons, right? And then you have 3 unpaired electrons. So that's what you should end up with for nitrogen. So what we're going to do is we'll do sodium, okay, and then we'll talk about sodium ions. So sodium is in group 1. Hopefully you knew that. So Na is group 1, right? And so it just got one dot. It doesn't matter where you put the dot. Now, if I want to make sodium ion, right, then basically I just have to remove an electron. So I'll go like this, and I get Na plus. Now, if you do chlorine, chlorine's going to look like this. I'll have 7. So go back just so you can see this. You'll have 7 valence electrons. So chlorine's in group 7, right? So over here, or 17, and it's going to have 7 valence electrons. And go back here, and I'll write 7 here just as a reminder. We looked that up. So I'll do Cl, and then what I'll do is I'll go like this. I'll go 1, right? 2, 3, 4, 5, 6, 7. And what you should have here now, because you have 7 electrons, is you have all these pairs. They'll often call these non-bonded pairs. We'll see that in structures. They'll call them non-bonded pairs. It turns out those don't usually end up bonding with any other atoms. It's the unbonded electrons the unpaired electrons that end up bonding with things usually. Okay, so we'll have 3 pairs, right? 3 pairs, and then 1 unpaired. So that's basically how that works. Now for chlorine, if I wanted to make, for example, chloride ion, then I have to add an electron. So on sodium, I subtracted an electron. On chlorine, I'm going to add an electron, and I'll end up getting like this. I like drawing the last one like that one as a different color. Okay, so think about that. Like this represents the 8, right? And if you think about how many electrons chlorine would have if it picked up 1 electron, we'll go back over here. You'll see chlorine picking up 1 electron will have 18 electrons. So that makes it have that noble gas electron configuration. So remember, the noble gases get their name because they're relatively unreactive, and they get that. What that causes them to behave like is that they don't react with elements usually. So that's why they are called noble. They don't react or interact with the common elements, all the other elements, right? It's probably a bad thing to say these days, but anyways, that's the way it's usually phrased. Okay, so chlorine ends up having a noble gas configuration. But what about sodium? Because sodium lost an electron, right? So chlorine is going to have the same electron configuration as argon. So this is the core notation. Remember that? So what about sodium when it loses an electron? So let's go back, right? So sodium's right here. Right, it's got 11 electrons, so when I lose an electron, it's going to look like neon over here. So it's actually doing the same thing. By losing an electron, it's getting its outer shell to have 8 in it, that is neon's electron configuration. So this is going to look like neon. Be isoelectronic is the term. Actually, I'll write that down for you. With. All right. So it has this, isoelectronics is a fancy way of saying it has the same number of electrons and arranged in the same way as a noble gas. Okay.